a pleasure to have Mar González from Madrid, and she will tell us about Pohozaev identity for the spectral fractional Laplacian.
Okay, so thank you. Well, thank you for coming. Thank you, Asma, for inviting me, and it's always very nice to be back to Cambridge. And okay, the topic today is Pohozaev identity, and I will be concentrating on the spectral fractional Laplacian. So when you see spectral, there are eigenvalues here. Okay, so let me just give you a quick review of the usual Pohozaev identity, just the classical one for the Laplacian. So I start with a domain in Rn with dimension greater or equal than 3. So Pohozaev identity was developed to study the following problem. Just this is a semi-linear equation for the Laplacian, and let me just write the zero degree conditions on the boundary of omega. So it was, I'll write the statement. That's just 2 minus n over 2, the integral of omega u minus delta u. So let me write the energy terms, minus the integral in omega x nabla u minus Laplace of u equals. So what I have here on the left are some energy terms, and the Pohozaev identity, what's telling me is that this is only a boundary term, and moreover, in many cases, this thing has a sign. Here, nu is the exterior normal to the domain. Okay, so this is the classical identity. Just let me set up some notation. I'm going to call this Q1 of u. The 1 is for just the Laplacian, because I'm going to switch this to a different power. And the corollary is that if omega is a star shape, that means that, okay, you have a point that can link, well, maybe every point in the boundary. Okay, maybe this wasn't a star shape, but you get the idea. Then this x dot normal always has a sign. Okay, I'm thinking that is star shaped with respect to the origin. So this term always has a sign, and then we have that Q1 is non-negative. So in particular, another corollary is the non-existence for problem star. If, okay, let me, in all these conditions, if I take a nonlinearity that satisfies 2 minus n over 2 u f of u plus n capital F of u. Here, capital F is a primitive of little f. So if this is negative, then no solution in the classical sense. And the proof of this is quite easy. Just go back to this identity, change the Laplace by f of u, make some integration by parts. You will have, by hypothesis, that this Q1 is negative. This is always positive contradiction, and then unless you are, okay, maybe you are trivial solution if you have f of 0 is 0. Yes, everything is under a star shape. So for my, and I'm looking at classical solutions. So the proof of this, maybe I will skip it, but it's a a classical calculation that relies on just some vector calculus. The proof of the classical Pohozaev identity, you start with a very, okay, I'll write it a little bit, x dot nabla u, just this, let's say, happy idea that you find some divergence-free term, okay, not divergence-free, but almost, over 2 u square minus x dot nabla u times Laplace of u. Okay, just take this identity that you can check it by hand, give it to your first year calculus student, make sure they don't make a mess with the subindexes, but in any case, integrate this and you get that, you get this directly. Okay, and an example of non-existence where this can be applied. You're interested in this equation for power nonlinearity. That's the first thing that you can look at. If you take f of u to be u to the p, just p minus 1 times u, then this theorem can be applied. This restriction here tells you that you are in the supercritical case. So now the critical and the subcritical case is another story, but at least you have non-existence in the supercritical. Okay, so this is the classical picture. Let me move on to the fractional world. So I'm going to define first the fractional Laplacian on Rn. So I will have to restrict later to a domain, but for now let me work on the full Euclidean space. Now the fractional Laplacian is just an operator that I'm going to denote minus Laplace to the s. Here s is any power between 0 and 1. And it's an operator that under Fourier transform, it has symbol c to the 2s, the Fourier transform of u. Now, if you have s equals to 1, this is Laplacian, this is c squared, so you see the analogy. It can also be defined as a singular integral. So the fractional Laplacian of a function at a point x, there is some constant, there is some principal value that I'm not going to talk about, and then you need to integrate the convolution with this singular kernel, minus y to the n plus 2s dy. Okay, and the first observation is that to calculate, this is not a local operator, because to calculate the value of the operator at a point x, contrary to the usual derivative, you need to know the value of the functions at every point y in Rn. So you are not only seeing the local behavior of the function near a point, but you are seeing the behavior of the function far away. And this is going to be a bit of headache, because you cannot use a standard cutoff argument. When you cut off, you will get lower order terms coming from this integral in the whole Rn.
Is it true that the s equal 1 is the formula for the usual Laplacian?
Yes, except that here there is a c of s, and there is a compensation. You need to take this limit properly. So the proof is, take this, take a Taylor expansion, and you have, I'll do it, u of x minus u of y. This is like nabla u of x, x minus y, plus t squared u x. Well, let me write it formally like that. This goes away because of parity considerations. And this one, you have many terms here, but most of these cancel because of parity considerations, and you pick up only the diagonal terms here, when you pass to the limit s goes to 1, there is some cancellation between the constant and this integral, and you have the proof. Okay, you can also, okay, a semi-group formulation, but I don't need it. Now, how low can I write that you can still see? Maybe
Maybe you can swap it.
I'll swap. I forgot to say that this is joint work with Itaiza Barrios Cubas, which my PhD student, Mateo Monforte, Autonoma, and Clara Torres La Torre, who is a PhD student at ICMAT. Sorry, a postdoc at ICMAT. Okay, so now let me write definition of the fractional Laplacian on bounded domains. So I start my omega in Rn, bounded, star shape, whatever, smooth. Okay, and now since the fractional Laplacian is a non-local operator and it's seeing everything that is happening around, there are several reasonable definitions that you can give of this operator. So the probabilists know much more about this. So they know about subordination, killed processes, etc. Let me just give you the PD, the PD version. Okay, the first one is the restricted fractional Laplacian. Okay, so I just take the original definition. Okay, it's the same thing definition up there, but take functions that have a support inside omega. Okay, second thing that you can do is the censored version, in which, okay, CFL, take the same definition, but take the integral only in omega. So you are not seeing, so okay, same definition, but instead of integrated in Rn, you integrate in omega. And this little difference make them behave very differently. For instance, they have different boundary regularity. There is a big story, a long story about it.
Different boundary condition, Dirichlet or Neumann type for fractional, because here it's compactly supported and there.
Yes, kind of. I mean, the thing is that once you set up your, so obviously this one you want Dirichlet conditions, but you could also ask this one with Neumann conditions. So they are not, it's not, you can give additional boundary conditions in addition to this. So what is different is kind of the boundary behavior. So for instance, here, let's say, well, I'll talk about the boundary behavior in 5 minutes. But yeah, another story is like, what is the right boundary condition to put here? And that's something I'm trying to look at. Anyway, let's get to the one that I'm going to be working in this talk, is the spectral fractional Laplacian. And it's actually, from the spectral point, I mean, it has a very nice definition. So let me take lambda j and phi j to be the eigen values and functions for the standard Laplacian in omega with Dirichlet boundary condition. So this means that the Laplacian of minus Laplacian of phi j is lambda j phi j phi j equals 0 on the boundary of omega. Let me take them normalized, orthonormal, all the nice basis. So you can write any function u as the sum, as a linear combination of this phi j. Let me call the Fourier coefficients uj hat. So then fractional Laplacian, the spectral version, the spectral fractional Laplacian is going to be, okay, this it's the same basis, the same Fourier coefficients, but I'm applying the operator to the s, so I need to write eigenvalues to the s. And this is my definition, but it's the spectral power of the Laplacian, nothing fancy. And these three operators are different. So for instance, let me just write some differences. For instance, the restricted of U, it also has a formula in terms of as a convolution with a singular kernel, like the one for Rn that I have already raised. But you have a different kernel. No, okay, no. Here the kernel is same. I mean, sorry, it's just you are taking functions that have compact support. But when you go to the SFL, then okay, you can give also a singular integral formula, but so here you only live in omega. But you have here a new kernel, and you have an extra term. Okay, u of x, u of x. Now the difference between these two kernels is that, okay, when x is close to y, they have the same singularity, but while this is positive in the whole Rn, so which is nicer to when you are going to do comparison principles, positivity, etc., this operator degenerates at this kernel degenerates at the boundary. So that's a bit of a headache. And now this one, so okay, this degenerates at the boundary. This one here, and okay, there's no u here. This one here blows up at the boundary. So let me let d be the distance to the boundary of omega. ds or 2s, t2s. So it blows up at the boundary. So it's a little bit headache of an operator. Now, this kernel is invariant under translations. This kernel is not invariant under translations. So if you are trying to look at invariances, it's completely different. And also the boundary regularity is different. I will write it here because it's boundary regularity. Let's say for solutions that vanish at the boundary of omega. So for the RFL, basically you know that u divided by the distance to the s is a C alpha function. So this means that at the boundary functions arrive like the distance to the s power. It's a Holder function, but not smooth. While for the spectral fractional Laplacian, this one, well, it's even better than C0. I mean, you can put C0 and that's enough, but you can even say 0 alpha. Ellipses. While these ones are ellipses. And let me quote, well, for the semi-linear or even just put NEF. So I'm looking always at this equation equals f of u or something, but just equation with the operator. Now, the boundary regularity was written in a paper by Onforte, Pigali, and Vázquez. So, so I think they studied this very carefully. So anyway, these two are very different operators, and why do I'm telling you so much about the RFL? Because my objective today is to talk about Pohozaev identity. So there is a famous paper by Rosotan and Serra that was part of the thesis, and it was now it's become a classical paper. Okay, so Rosoton, so Pohozaev for the restricted, and this is the paper by the classical paper by Rosoton, Serra, 2014, and then there is a later paper by Group. I'm not sure how to pronounce it. Group. Okay, sorry, don't tell her. Okay, they prove a Pohozaev identity for the restricted, and if you, I already delete the classical one, but if you replace the Laplacian by the fractional Laplacian, you get the same energy term. Except that you have a different boundary term here, okay, there's some constant, but still it's, before we had here the normal derivative, now it's not the normal derivative, but it's something that replaces the normal derivative and which agrees with the regularity that I presented up there. So u behaves like the distance to the s, so then this is a smooth function up to the boundary, and this is your replacement of boundary of normal derivative. When you go s equals to 1, you get u over the distance. It's kind of the standard derivative. So it's all very logical. The proof is not easy, but basically this is the same identity as the classical one, putting an s in various places. But the proof is also the proof is not easy. Anyway, so okay, do I have?
Yeah, but we are on the boundary, so it is zero.
No, it's sorry. This needs to be taken as the limit because up there is well defined. Now the proof of this, well, maybe I'll skip it because it's very different from the one that I'm going to present now. If I have time, I can tell it, but it's an integration by parts, kind of integration by parts, which is not trivial. Well, and also a control of the boundary term plus boundary regularity. Okay, let's say that the hardest part in the Rosoton paper and Serra was to develop the boundary regularity. Smoothing. I don't remember what is the sharp thing, but it should be smooth. No. there is a sharp boundary regularity, but I don't remember. So
But does the proof involve the construction of some vector field that basically looks normal at the boundaries? Like, do you need some maybe C11 regularities, C2 regularities?
yeah, well, I think for these ones you construct sub and super solutions, so you need C11 because you are putting balls in, you are touching by balls inside and outside in the proof. But this is an old proof. Maybe it has been improved.
But I think that explains the role of the vector field.
Sorry?
I think it explains the role of the vector field, right?
Yes, so this is stated with X as vector field. There is a general form with another vector field
Yes.
that you can put. Okay.
Yes, but the thing is that you need to be a very here. The thing is that here you are using the vector field X, which lives in the whole Rn, and the trick is that you are able to go from Rn to omega. But X is your vector field. There are other vector fields. You can do this on manifolds with symmetries, and then you will get another Pohozaev identity. And then in geometry, you have the Pohozaev chain, which is very general, and it involves killing vector fields on a manifold. But so this would be kind of the flat case with a conformal metric Gu equals U to the 4 over n minus 2G. I think there is some notes by Raskin which explains all this very clearly. But anyway, let's go back to the fractional world. In the fractional world, we cannot use X as a vector field because the operator is not translation invariant, nothing invariant. So we lost all the invariances in Rn. And actually, when we try to, well, maybe there is an idea of this proof that is going to, that is kind of inspiring, is that, and then you will see why it doesn't work, is that in the proof, they rescale u lambda equals u to the lambda x, where lambda is greater than 1. And they wrote, for instance, let me pick up this term here. You can write it as the derivative with respect to lambda at the point lambda equals to 1, u lambda times the integral of minus Laplace s of u. So you are using these invariances of the problem, this invariance and the rescaling. So that makes it more apparent. This is another way to prove Pohozaev, by the way, to use it's kind of the Netterian approach, to get invariance, that the invariances of the equation by dilations, for instance, gives you integral identities. But sorry, this was a little bit digression. Anyway, when you expand this, you will end up with the energy terms, and you will arrive to the boundary term when you integrate by part somewhere. Anyway, so forget about all this because it doesn't work for the spectral. It's what I would like to talk today. So let me state the theorem. Pohozaev for the spectral fractional Laplacian. Okay, here we are going to be very generous with the regularity of u. U needs to be in H0, and let me be very generous, take 2s p over 2 omega. This is too much, but this is at least what you need to have all the terms that I'm going to write down make sense. Okay, so let me define this energy. So integral omega u minus Laplace. Here it's, even if I don't write it, it's from now on, it's going to be the spectral fractional Laplacian. Omega x dot nabla u minus delta to the s of u. So if you look, this is the same energy as we had before. Let me call this QS, as I did in the classical case. And what we prove is that that QS, the fractional energy, the fractional Pohozaev, let's say, energy, can be written in terms of the local counterpart times some transition matrix. And this thing here is a Schur product. And you are not seeing matrices here anywhere. And okay, I'll write down everything in a second. And this PS is positive definite. So, okay, so okay, in the original Pohozaev, this was equal to a boundary term. Now we don't have this, but we can still go from the non-local case to the classical case Q1, for the case for the Laplacian, by a positive definite matrix. So when you are going to talk about the sign of this thing, let's say in star-shaped domains, this is not going to change the sign, and then you will get positivity. I'll write down in a moment. So what do I mean by a Schur product? Is that we realized that both Q1 and QS have an underlying quadratic structure. So you can expand this in eigenfunctions and in our basis, and then this can be written as, remember these were the Fourier coefficients of U, because and then you have, let me call this matrix UKS, let's say, no, this one should be 1, and this one should be UJKS UJ UK. So remember that I'm calling this the Fourier coefficients of U for the standard basis. So both Q1 and QS have a matrix, a quadratic form structure, where we have with these two matrices here. And actually what I'm writing here is that this matrix can be obtained as the Schur product of these two matrices. Now the Schur product is the student's dream. The Schur product is to do is to multiply component wise. And the PS, I'll write the formula in this corner. Okay. PJKS equals lambda JS minus lambda KS over lambda J minus lambda K. Well, if lambda J is different from lambda K, just take your Dirichlet eigenvalues and you get that formula over there. And then when lambda J, if you have multiplicity, then you have L S lambda J S minus 1. S minus 1 if they are equal. Okay, so this is the theorem. I'll give you the proof now. So when we started this problem, we thought that we could give a PDE proof as following, and actually we thought it was an easy problem for our student, and say, okay, do this, change the proof by Rosoton and Serra, and that's it. You have an easy problem for as a first thesis problem. And then except that it wasn't easy. Because the boundary regularity for both problems is very different. And we were not recovering the boundary term from the boundary term on the right-hand side. So we had to start with a new idea, and the short product was quite useful. Anyway, before I give you the proof, you have corollary that is going to be non-existence for this problem. Let me call minus Laplace S of u equals f of u in omega star shape with Dirichlet condition 0 on the boundary of omega. Then if we have some relations, some condition on the nonlinearity, so if this is negative, okay, you have to exclude the zero u identically 0 case. Then no non-trivial bounded solution. And the proof of this is quite easy in the light. The proof is if you are in a star shape, you know that Q1 had a sign. This was the classical Pohozaev. You apply Schur product theorem. And if you have the product of a positive definite matrix and another positive definite matrix, well, let's say non-negative, then also QS of u is non-negative. And then you arrive with a contradiction like this contradicts that. And that's it. That's the end of the proof. Same thing as the classical case. There is nothing deep. Just apply Schur product theorem. Okay. So now we can go to the proof of the main theorem. Maybe I prefer to erase this and leave the theorem on top. This is not so important. So you will see that the proof is quite easy. It's just a little Fourier expansion calculation, except that it was one needed to get this tricky idea. So, so let me give you the proof of the main theorem. And the first thing is, okay, take your QS to be that expansion and there and write it in expand it in Fourier. Or write your u to be the sum of the uj hat by j and substitute this, calculate, use that these guys are eigenvalues of eigenfunctions, and what you will guess is 2s minus n over 2 times the sum, that is a lambda k to the s because of the fractional Laplacian there, and then there is uk squared. Just for the first part, using that the eigenfunctions are orthonormal, so you have only the k sum minus the integral in omega. Here you have to, sorry, not the integral in omega. I'll write it later. You have a fractional Laplacian, you have a lambda k to the s. Okay, you have a term that you have to expand, uk hat, uj hat, and then the integral in omega of the x dot phi j phi k, just for the second one. So you are almost able to expand this in they are eigenfunctions of the Laplacian. So minus Laplacian of phi j equals lambda j phi j, and I'm taking a normal basis. Okay, so this is just substitute your Fourier expansion, and you have to do something with this. But you see there is nothing fractional here, there is no s. So you can use the classical Pohozaev identity to handle that term. And this is a lemma that tells you that actually you can calculate this term, and it's minus n over 2 if j equals 2k. Let's assume there is no multiplicity for now. Then you have to do something if you have multiplicity, but it's only a technical thing. And okay, the classical Pohozaev relates an energy inside with a boundary term. So when you apply the classical Pohozaev to the eigenfunctions, what you are obtaining is a boundary term, Pj times increment Pk x dot mu. So you are able to use the classical Pohozaev. You have to apply classical Pohozaev both for phi j and for the sum of phi j plus phi k and maybe a few lines of calculations. But this allows to go from this interior energy term to a boundary term on the eigenfunctions. Okay, let's assume that this thing is non-zero, otherwise you have multiplicity, there is something to be said, but that's not important. And that's okay. So I want to find a formula. So you see the theorem is that QS can be related to Q1 by a positive matrix P. So, okay, I need to find the coefficients of the quadratic formula here back to the quadratic formula for the classical case. And okay, I'm almost there. I have expanded this, and this gives me a first formula. If you look, what this is telling me is that the coefficients for the power s, okay, here there is, you need to rearrange all this. But what you have to, I didn't tell you, is that this thing is precisely the q jk in the local case, because there are no fractional powers here. So this is the formula that relates your qs with your q1. Let me write it down a little bit cleaner. So this is just a straight formula calculation. Some delta j plus 1 minus delta. Okay. Okay, I have to do one thing first. So I have already written this as the sum jk of some q jk tilde of s uk tilde uj tilde. Okay, I mean, just pick up the coefficients from this formula. And you have a formula for this q tilde. I will not write it down. The problem is that q tilde is not symmetric. So let me symmetrize. By taking qjk s to be 1/2 q tilde jk plus q kj tilde s. So once you have symmetrized, then you have that this is the formula that I wanted, where this qj, it was the most technical part of the calculation is the formula that I was writing before, delta ik, so minus delta kj over 2 lambda j to the s plus lambda k to the s or lambda j minus lambda k and the integral of this boundary term that you relate to q1 qj1. Okay, so this was a little bit technical, I'm sorry, but this gives you the proof of step 1, a formula that relates qs, the coefficients of the quadratic form for qs, to the coefficients of the quadratic formula of q1. Now that's for 1. Now let's for 2. Okay, there is I need to prove that your P is positive definite. Maybe I don't need this anymore. Okay, at least semi-positive definite. So the proof of 2 is that to prove that P S is positive definite, well, let's say non-negative as a matrix, we use Wagner's theorem. So let's state Wagner's theorem in case you ever need it. If you have, okay, let me state the Wagner's theorem in abstract. If you have that this mu j minus mu k is positive for every c and for every mu j, essentially you have a matrix of a very special form and you are saying that this matrix is positive definite, then this is equivalent where h is a function. This is equivalent that there exists mu positive bounded regular measure such that h of t is the inverse transform of this measure. So that's what the theorem. So, well, the only thing we have to do is to take this Pj, write them in this form, and take its Fourier transform and check that the Fourier transform is positive definite. And okay, to write the Pj in this form, you have to do some changes. So you have to define lambda k to be e to the 2 mu k, and then you define your h of t to be the sinus of st over sinus of t. Then this is essentially pjk of s for this choice of mu and for this choice of h, and then take the Fourier transform of this. The Fourier transform of this is non-negative, and that's the end of the proof of the claim 2. Okay, let me make some final comments. We wanted to see that this P is positive because we wanted to have or to exclude the equality case, but we couldn't because when you go to the Schur product, you need an infinite dimensional Schur product, and we haven't found a proper reference, like what is the condition that if you have a Schur product to be 0, can you say that one of them is 0 in infinite dimensions, and that we haven't found, so we cannot exclude the equal to 0 case, and I think this is the end of the proof.
Any question, comment? Yes.
So you mentioned that there were problems with boundary regularity in this proof, as far as I understood. Which in particular?
So in the Rosaton-Serra proof, for the but basically for the restricted fractional Laplacian, you know that u over the distance to the s is C0. Well, it's actually sharp C alpha. This is sharp. You have, at some point, you have to calculate this for a function that vanishes at the boundary. And this gives you C1 log B plus C2 times B times u over D plus dot dot dot. So when you are just playing around and you have your interior terms and you try to pick up, okay, what would be the kind of the boundary term? Here you pick up a boundary term because you have a single, this singular terms appears at some point, and this is exactly what gives you the boundary term. Because somewhere in the proof you are using that for solutions of this problem, this is singular. You are picking up a singularity which yields that boundary term. So I'm not giving you all the steps of the proof because this is quite long, but that's the idea. This is singular, so, and this is what will appear when you do the integration by parts. In our case, solutions are Lipschitz, so that's it. We were not seeing anything when we tried this proof. So it was all the boundary terms were 0.
Problem was too much regularity.
Yes.
Okay. Okay. Thanks.
Yes.
Can one try to start with a different basis, like a Neumann eigenfunction instead? Makes sense. Sure, but I mean, the definition seems to use that there is a spectral eigenfunction, so
Yes, what we're doing is that since we're taking spectral powers, then you are relating the Q to the Q1. I think if you have a basis, and okay, you are using that you have a common basis of eigenfunctions, and that eigenvalues are lambda and lambda to the s. So what is the operator that arises when you take those? I have no idea, but it's quite interesting.
maybe the difference between the one with Dirichlet minus the one with the Neumann. I don't know. So,
No, okay. I don't know if this one with Neumann has Pohozaev, but probably you can have this relation to pass from local to a spectral power. I think this will be the same.
Any other questions? So you think that this definition is kind of the more natural one, what one really, I mean, because it's, you said that there are three different, the end of the three different the way that you.
No, I don't know which one is the best one, so I don't claim this is the right one. It depends on what you are modeling. So I think Matteo has a very nice example in which you have diffusion in a domain, and the diffusion is modeled by mosquitoes moving around, and sometimes the mosquito dies when it touches the boundary wall. That is an electrified boundary, so fried mosquito. Sometimes the mosquito can jump and it fries when it arrives to the floor outside. Like, it depends on what you want to model.
And yours is the model of the diffusion.
So the mosquitoes are diffusing inside, but what is, I don't remember which one is the boundary condition that we put. Does it get killed? I would need to look at the three different definitions to see which kind of electrified boundary you have to put for your mosquitoes. But that's the difference.
So if not, let's thank Mark.